Hey everyone, today we're going to start chapter 14.3, and I've split this chapter into two parts, part 1 and part 2. In this section, we're going to learn about concentration and rate laws. So as an introduction, one way to study the rate of a reaction is seeing how the rate changes with changing the concentration. So remember, we learned that typically the more concentration that's added, typically the rate of the reaction is going to increase. Down below is a data table that was taken by reacting ammonium with nitrate ions in water and determining how fast that reaction was happening. And they did a number of experiments. They changed the ion concentration for ammonium and for nitrite, and then they measured the speed of the reaction. So in that, we're going to see that when NH4 or ammonium doubles, the rate of the reaction doubled. So for example, here, if I went from 0.01 to 0.02, it's doubling. We're going to notice that my reaction here doubled as well. And we're also going to see that when NO2, -1, doubles, we are also going to see that the rate doubles again. So if we look back at this match, here, if we see from 0.0204 to 0.0404, notice I'm doubling it there. We're going to see that the rate again doubles, 10.8 to 21.6. So we can actually use this information to calculate something called a rate law or an equation for determining the rate of the reaction. So what is rate law? Rate law is an equation that basically relates the reaction rate to the concentration of reactants and sometimes the products. So it allows us to take into account how does concentration affect the speed of a reaction. So for the general equation, lowercase a, capital, etc., remember that lowercase is going to be your coefficients, just like yesterday. And capital letters, this is going to be your compound that you're working with. Generally, a rate law takes the following form. Rate equals K, and K actually is called a rate constant, and we're going to learn how to calculate that in tomorrow's lesson. The rate constants are affected, or the number for the rate constant is usually affected by temperature, which is another thing that affects speed. Here we have brackets, which stands for the concentration of our A compound to the M power, and then our concentration of our B compound to the N power. And now the exponents M and N are typically small whole numbers, and they are not the coefficients. I'm going to teach you in the next couple slides how to find M and N, but just know they are not the same as the coefficients. So when I talked about M and N, these are called reaction orders. So the rate law, again, remember, is K of your reactant to the M power, and then times reactant 2 to the N power. Again, M and N are called reaction orders, and oftentimes, in order to figure out what your rate law equation is, it becomes one of determining, well, what reaction order are M and N? Typically, in most reactions, M and N are either going to be 0, 1, or 2. So, how do I go about determining, is M 0, is it 1, or is it 2? And that's going to be looking at data. So we classify something as a 0 order is if when we change the concentration, it has absolutely no effect on the rate. So example of this is if I double the concentration, the rate stays the same. A first order reaction, this is when you change the concentration, it's going to be proportional to changes in the rate. So that means if you double the concentration, the rate is also going to double because 2 to the first power, first order, is 2. If you triple the concentration, 3 to the first power means it's going to triple the rate. Even if you quadruple it, 4 to the first power, it is literally just going to quadruple the rate. It's going to be proportional. Second order is changes in the concentration are going to increase by a factor of 2. So, for example, here, if I double the rate, 2 to the second power, it's going to quadruple my speed. If I triple the rate, 3 to the second power, it's going to increase my rate by 9-fold. Same thing as if you quadruple the concentration, 4 to the second power, it's actually going to take my rate to the 16th. Also note that the overall reaction order is the sum of the order. So if I wanted to know what was the reaction order for the entire equation, we're just going to add m plus n to tell me my overall reaction order. Now, rate laws must be determined experimentally, so in order to calculate m and n, you're going to need data. So here is the example that we looked at the beginning of the lesson. We have data. Remember, our general rate equation is K times the concentration of A to the m power, B to the n power. I'm going to plug in my A, which is NH4, because that's what I'm given initially. And I'm going to make my B my NO2. So I'm going to plug that initially in. Now it just comes down to determining m value and n value. So how do I go about doing that when given data? Well, first, we want to be able to evaluate NH4, and we want to make sure that we're only looking and changing that value. So we want to look for something where nitrite concentration stays the same. So for example, in experiment 1 and 2, we're going to see here, this is when nitrate stays the same. This allows us to actually focus on ammonium and determine it. So here, when we're focusing on ammonium, we're going to see that here, this doubles. And we're going to look at our reaction rate, and we're going to see that this doubles as well, which tells me that since this doubles and this is proportional, it doubles as well, this is a first order reaction. If we wanted to look at the effect of nitrite, we're going to have to look at nitrite changing whenever NH4 stays the same. A good example of this is experiments 4 and 5. In experiments 4 and 5, these stay the same, which allows us to evaluate these numbers here. We're going to notice here it doubles, and that means here it doubles. So again, the reaction doubled, or the concentration doubled, the reaction rate also doubled. This indicates a first order reaction. So the way that you could write it is by putting 1 in for those exponents, or note that if the exponent is 1, you can just omit it and just write it as such. So here are 2 examples that we're going to walk through for your notes. These examples are actually at the end of your notes since I have part 1 and part 2. So please flip to the end of your notes where this is going to be set up. It says determine the rate law from the initial rate data. So you're given data over here to the right. And we want to figure out what is the rate law of the reaction. So let's set up what I know. I know that the rate is going to be equal to K, which is always going to be there, the concentration of A, since that is what I'm given over here, to some kind of m power, times the concentration of B to some kind of n power. And so I need to figure out what is going to be m and n. So let's focus on A first. In order to calculate what A is going to be, B has to be the same. So what I'm going to do is, if I'm going to look at A, I'm going to focus on experiment 1 and 2. 1 and 3. And the reason I'm going to focus on 1 and 3 is because that is when B stays the same. So here, between 1 to experiment 3, we're going to notice that this amount doubled. And the way you can check it is just to take 0.2 divided by 0.1. So we're going to see here that the reaction doubled. And I need to find out what this exponent is going to be. And then we're going to look at what happened to the rate of the reaction. Here, we're going to notice from 1 to 3, my rate, if I take 16 times 10 to the negative fifth, divided by 4.0 times 10 to the negative fifth, you're going to notice that it actually quadrupled. So if I double the concentration, I quadruple the rate. So 2 to what power gives me 4? And you're going to notice that 2 to the second power gets me 4. This tells me that for my rate law, my concentration of A is a 2. Now let's focus on B. Here, we're going to look at experiments numbers 1 and 2 because that is when A stays the same. So we're going to that allows us to focus on B. Here, notice that this doubles. So we're going to have 2 to the x, and then we have to look over here. Well, we're going to notice that our reaction rate stayed the same. So it's just a 1. It stayed the same. So 2 to what power gives me 1? And you're going to notice 2 to the 0 power gives me 1. So that means that B is a 0 order reaction. And whenever something's a 0 order reaction, you don't have to write it. You can omit it. So my rate for this one is as follows. So remember, my overall rate order is M plus N. So M we found was 2 plus 0. My overall rate order is 2. Okay. Here is another example also at the end of your notes. If you want to pause the video and try to solve this one on your own, you're more than welcome. And then we're going to go through the answer. Okay, so let's try to go through this. Let's set this up. Remember, rate equals K. And we're going to plug in our first one, which is the concentration of NO to some kind of M power, times the concentration of H2, because that's the other one in the data set, to some N power. And so we need to figure this out. So if we're focusing on NO first, we're going to look at reactions where H2 stays the same. So H2 stays the same between reactions 1 and 3. So those are the ones we're going to focus on to allow us to look. So here, between reactions 1 and 3, we're going to notice that the concentration of NO doubled. And then we have to focus on the rate. Well, if we take 4.92 and divide it by 1.23, we're going to notice the rate quadrupled. So 2 to what power gives me 4? And we're going to see that 2 to the second power will give me 4. So NO is a second order reaction. Okay. Now let's focus on H2. We want to look at reactions for H2 where NO stays the same. So NO stays the same between reaction 1 and 2. So we're going to focus on 1 and 2. So here we're going to notice that this one doubles. So I'm going to put a 2x. And then over here, we're going to notice for our initial rates, that also doubles. So 2 to what power equals 2? And you're going to notice 2 to the first. So you can write H2 just like that, or you can put a little 1 out here. Either one is correct. Okay. And then if I asked you to find the overall rate order, remember that is M plus N. So that is 2 plus 1 equals our overall rate order is a 3. It's a third order reaction. And that is the end of today's lesson. If you have any questions, please make sure you ask. And otherwise, I hope you guys have a great day.